Hello, my name is Gio, and this is my CS4220 final project. My project is GPU Accelerated Image Histogram Equalization for Contrast Enhancement. The goal of this project is to take a grayscale image with lower contrast and improve the contrast by redistributing pixel intensity values across the full 0 to 255 image. I implemented both a CPU baseline version and a pseudo GPU version so I could compare correctness and performance. This problem is a good fit for GPU computing because image data contains many pixels and many operations can be performed independently across those pixels. The GPU version uses parallel kernels to compute the histogram, build a cumulative distribution function, and remap the pixels. The overall pipeline has 5 main steps. First, the program generates a synthetic low-contrast grayscale image. I chose this approach so the project does not depend on external image libraries like OpenCV, which makes it easier to compile and reproduce. Second, the program computes a histogram of the grayscale intensity values. Since this image is grayscale, there are 256 possible intensity bins from 0 to 255. Third, the histogram is converted into a cumulative distribution function, or CDF. This is done using a scan style operation. Fourth, the CDF is normalized into a lookup table that maps old intensity values to the new equalized intensity values. Finally, every pixel is remapped using that lookup table to produce the equalized output. The CPU implementation performs the same pipeline sequentially. The GPU implementation parallelizes the expensive part using the pseudo kernels. The main code is inside main.cu. The CPU baseline is implemented in the histogram equalization CPU function. This function computes the histogram, builds the CDF, normalizes it, and remaps the pixels on the CPU. The first main pseudokernel is histogram kernel. In this kernel, each thread possesses pixels from the image and updates the corresponding histogram bin. Since multiple threads can update the same bin at the same time, I used atomic add to keep the histogram correct. The next kernel is scan CDF kernel. This computes the cumulative distribution function from the histogram. Since the histogram is only 256 bins, this can be handled in one pseudo block using shared memory. After that, the kernel creates the lookup table used to map original intensity values to equalized values. Then remap pixel kernel applies the lookup table to each pixel in parallel. This final remapping stage is very data parallel because each pixel can be processed independently. The program also uses pseudo events to measure the GPU execution time. The CPU time is also measured so the final output can report CPU time, GPU time, and the speedup. Now I will compile and run the program. The program prints the image size, pseudo device, correctness check, timing results, histogram summary, and a sample pixel comparison. The correctness check shows 0 mismatches greater than 1 intensity level, so the CPU and GPU outputs match the results as passed. In this run, the CPU time was about 43 milliseconds, while the GPU time was about 4.72 milliseconds. That gives a speed up of about 9.1 times. This shows that this GPU version successfully accelerates the histogram equalization pipeline. The main result is that the pseudo version produces matching output compared to the CPU version while running significantly faster. The speedup comes from using the GPU to process many pixels in parallel. The histogram stage uses many threads to process the image data. The CDF stage uses a scan style operation over the histogram, and the remapping stage assigns pixel transformations across many pseudo threads. One limitation is that the current project focuses on grayscale images instead of full color RGB images. I did this to keep the program focused on the GPU acceleration pipeline. A future improvement would be to extend the program to support color images or optimize the histogram stage further using shared memory privatization. Overall, this project demonstrates how pseudo can be used to accelerate a real image processing task, combining multiple GPU computing concepts, including data parallelism, histogram computation, scan memory transfer, kernel launches, and performance benchmarking.